We'll finish up Chapter 6 with just some simple examples of using Gaussian quadrature to approximate integrals. As far as Python is concerned, for Gauss-Legendre quadrature, for example, you will find two functions, Gauss nodes and Gauss quad, which are shown on page 225 and 226. I'm not going to go through the details of how the nodes are specifically generated, but they're similar to the lecture in the previous lecture where it involves root finding and actually involves solving nonlinear system of equations. But for our purposes, we'll note that this function, Gauss nodes, would return the nodes and the abscisses and the weights for the particular Gauss-Legendre quadrature rule that we need. X would be the abscisses, A would be the weights. You specify the number of functional evaluations or the how many points, you could say sometimes, that you want to use for the rule. And then there's a tolerance that's needed to solve the corresponding nonlinear system of equations to a certain accuracy. The default value is 10 to the minus 9. And then the Gauss quadrature function, basically, you supply the integrand, the function you're trying to integrate from A to B, and then again the number of nodes and weights that you have for your rule. And that's a simple, that's all you have to do, again, to do Gauss-Legendre. And to illustrate the use of those functions, we're going to look at example 6.11, which is on page 228 and 229. And the idea would be to determine how many nodes are required to evaluate this integral, 0 to pi of sine of x over x quantity squared dx, using the Gauss-Legendre quadrature to 6 decimal places. Keep in mind that the exact integral is 1.41815. So looking at the problem as specified in the textbook, this function, sine of x over x quantity squared dx from 0 to pi is the integral we were trying to approximate. We notice there's potential problem around x equals 0, but it's not going to cause any problem using the rule. We're not going to evaluate the integrand at 0. So in terms of getting an illustration of how to use those modules we mentioned earlier, and then we'll actually run the code, and I'll provide the code to you for you to use, both the Gauss quad and the Gauss nodes module, as well as this example. Basically, again, you have to define a function that would return the integrand that you're looking at, and we're using sine of x, and we're pulling it from the math library. So you could either import math and then just say sine of x, or get it this way, math.sine of x over x quantity squared. Return that for any given x. You were integrating from a to pi, and again, pi is available in the math library, so you can get it always by specifying the name of the library, .pi, if you want. And the exact interval, the exact integral we happen to know is 1.41815. And so for this particular problem, we're just going to loop over our range from 2 to 12, well, 2 up through but not including 12, of course, different numbers of functional evaluations or point rules. In other words, we'll take a 2-point quadrature rule, then we'll take a 3, 4, 5, up through an 11-point quadrature rule. And you call the function Gauss quad to do that. Gauss quad will use Gauss nodes to produce the nodes, and then we'll just see how well that integral approximation approximates the exact value, and then each time print out the number of nodes and print out what the integral value is. Okay. And it turns out the program output, as illustrated in the book, should be that the 5-point rule would be the first rule that would satisfy that error tolerance, and so the integral you can see pretty much matches, at least through those first 5 digits past the decimal point. It matches up beautifully with that. So let's look at the code itself and in the next segment. So here is the example 6_11.py file that I'll provide on Blackboard, along with the Gauss quad and Gauss nodes functions, so that you'll have those available to use. And again, this is just what we saw in the book. Very easy to apply the the rule with the particular number of nodes that are sought, and then compare that against the exact value and just see when that is satisfied, we'll print the number of nodes and what the integral is from the Gauss-Quadrat rule. So we simply run that. We should pretty much get what the book had, right? And it takes 5 nodes. We could go back and edit it if we wanted to make, you know, if, for example, we were willing to get a little bit rougher approximation and to make it 0.001 rather than than 4 zeros before the 1. Let's see how much reduction in the number of function evaluations we can gain. So the point rule would be slightly less, hopefully, and again, we could get the accuracy with just a 4-point Gaussian quadrature rule. In this case, again, it's Gauss-Legendre, but it only takes 4. So it depends on how much accuracy you want. It's going to determine how many nodes and abscisses you're going to need. So I've got another problem. This is problem 1 out of problem set 6.2 on page 230 of your textbook. You're asked to evaluate this integral from 1 to pi of ln of x over x squared minus 2x plus 2 dx. And you're told again to use Gauss-Legendre quadrature. And so again, we could use the same modules we had. And we're just going to set these up and show you how you would approach the problem, especially since you now have to do the transformation to use Gauss-Legendre. If the 2 parts of this problem is to use 2 nodes, that again means 2 abscisses, 2 weights, and then 4 nodes, which is 4 abscisses, 4 weights. A 2-point rule and a 4-point rule. To use Gauss-Legendre in this case, the weighting function is just a constant 1, so f of x must be everything there inside the integral. So f of x is indeed ln of x over that quadratic. And again, we are trying to integrate from 1 to pi of f of x dx. In order to use the Gauss-Legendre quadrature, remember that rule is based on integrating from -1 to 1, so you need that linear transformation, which was defined earlier. And so it's very important that you remember this transformation. It's going to come up every time you want to use Gauss-Legendre for something that is not integrating, for an integral that's not -1 to 1. So that's just very important. So the adjustment to the rule is like we had before in the previous slide. This is the rule then. It'll have to be b minus a divided by 2. Then using the weights from the Gauss-Legendre table or function from Python. But then you must take the corresponding abscisses from the table or that function and then plug them into this little equation to get each xi, which then goes into f. So you take f of xi, but xi is a transformation on the original Gaussian nodes. Why? Because you're not the original integral has to be mapped to -1, 1. So as ci, this Greek letter ci, moves from -1 to 1, in actuality for your integral corresponds to moving from A to B. Okay. So if we look at those 2 cases in the next slides, if you're using 2 nodes, you would then go to the you would either use the Python code or go to the table lookup, and you would remember, we had these in the notes before, those are the 2 abscisses, and then the corresponding weights are 1, and you must apply your transformation to get x0 and x1, plug those into the function, the integral, the function you're taking an integral of, and then appropriately scale. B minus a, b is pi, a is 1, b minus a over 2 is this, and you will get that approximation for 2 nodes. Very straightforward. Now, to go to a 4-node rule, again, you'd have to go in and pull out, these are all the nodes for Gauss-Legendre, then you have to plug them in the transformation, pi minus 1 divided by 2, you get this approximation, which you see is far different than the 4-node rule. And so that's just an illustration of of how the transformation is used and the mapping from an arbitrary integral AB into -1, 1. Key is don't forget this transformation. That's the function. The integrand is evaluated after you take the nodes or the abscisses and you plug them into that transformation. The weights will always be the same. That's not the problem. Finally, problem 6 in that same problem set 6.2 on page 230 illustrates how you could use Gauss-Chebyshev quadrature for a more complicated integral, which involves a square root function in terms of in the denominator term. What I've written on the top here is the Gauss-Chebyshev quadrature rule, where all the weights are the same, pi over n plus 1, and remember it integrates from -1 to 1. So for this particular problem, we need a transformation that will map the interval 0 to 1 to the interval -1 to 1, and that very simply can be accomplished by this very simple transformation. Let x be 1 plus t over 2, let's say. So, so what we're going to do is rethink of this rule that we have up here in terms of a different variable, just to keep it separate from the original problem. Like magic, I've changed it. I have rewritten the Gauss-Chebyshev rule in the variable t here. So we can see that we have to take an integral involving the x variable and transform it into an integral, say, like this, involving t. It just helps us understand this transformation easier if we represent the quadrature rule in a different variable. So will this transformation work? Well, as x is -1, you can show that that would correspond, as x is 0, you could show that corresponds to t being -1. Similarly, as if t becomes +1, x would become 1. So as x varies between 0 and 1, it's very simple, easy to see that the t variable will be appropriately moving between -1 to 1. So it's just making that transformation. Taking differentials then, of course, dx would be 1/2 dt, and what we've done is we transform with some algebra the original problem integrating in x to this problem integrating dt, and now we see our Gauss-Chebyshev formula, the left-hand side of it, very clearly, because f of t is going to be that numerator term, right? You can see it very clearly just looking again up here at the rule. F of t must be 2 plus t, which certainly is linear. Now, what does that mean, of course, is since it's just a linear function, and we know that Gauss quadrature rules are exact for polynomials up to the order of 2 to the n plus 1 degree, this will be exact. There will be no approximation. It will be exactly correct. And so then what we'll do is we'll just apply the Gauss-Chebyshev right-hand side as we've done here, use our function 2 plus t, where in this particular rule, though, you can actually come up with a closed form representation for all the nodes in terms of cosine. And then once you add up in this case, if you add up particularly any of the number of nodes for this particular rule, you know it's going to be exact. So if it's going to be exact for any number of these nodes up through 2n plus 1, then just for a single node, it'll be sufficient. So for a single node, we'll only have one particular value for t. It'll just be 1 t0 and 1 weight. And in that case, you can see when I is equal to 0, you're just going to have cosine of pi over 2, and then the weight will be appropriately applied as pi over 2, and then, excuse me, let me say it again. So if it's a one-node rule, this n is 0, so it's just going to be pi. So if a one-node rule, n would be 0, and so, and there will only be one particular abscissa, which would be this 0 corresponds to the I, so that's why you'll have cosine of pi over 2 times 0 plus 2, which is 2. Okay, so that's where this comes from. The fact that if it's a single point quadrature rule, then n is 0. And so the index here, it only goes from I goes from 0 to 0. All right, so there's only one point, so I will also be 0. And then the n there is 0, so the integral is 2 pi. And that's exactly what that, you can show that is exactly the value of that integral from 0 to 1. It is 2 pi. So that's just, sometimes you can exploit the fact that when you see that the f function could be a polynomial, you know immediately there's no approximation, it's going to be exact. And in this case, you could get at the answer by just a single node for getting an exact answer. There's no need to take a higher number of nodes. So that's going to be it for the examples that I wanted to cover. I'll provide some of the Python scripts that you can use again to do Gauss quadrature and get the Gauss nodes specifically for the Gauss-Legendre examples. And the rest of these rules work pretty much the same way. It's just different functions that you would need to return the nodes and apply the quadrature rule.